Hey, we're going to talk about sound a little bit. Just some real basics that, we want to get out of the way before we talk about sound in a little more sophisticated way. First of all, let's look at a sound. I have a really simple sound here. This is a tuning fork, which is makes what's called a pure tone. We'll talk in a little bit about why we call it a pure tone. And if we play this sound, do you notice how on the waveform, as the sound dies out, what changes? Well, it's how tall the wave is, right? The amplitude of the wave. And so loud sound, high amplitude, quiet sound, low amplitude. So loudness and amplitude go together. Another key characteristic of the wave has to do with pitch. Like, what does it sound like? Does it sound higher or lower? And I have a slightly higher tuning fork here. This one sounds like this. So let's go back to the low one. Okay, let's have a look at the waveform. We're going to start with the low one. Let's have a look at the wave. I'm going to do that again, freeze the wave. So if we take a look at this wave, it looks like one whole cycle, one peak and trough, one compression and rarefaction. That whole thing happens in like 3.8, 3.9 milliseconds. And that corresponds to about 256 hertz. So the frequency is 256 hertz. So that's our lower sound is 256. And here's our higher sound. And if we look at this wave carefully, and we see how long does it take for one cycle to happen, and I'm going to say it's happening in maybe 3.5 milliseconds. So old one was like 3.8 or 9 milliseconds, and now we're like 3.5 or 3.6 milliseconds. So this higher pitched, one cycle of sound takes a little less time to happen, and that corresponds to a higher frequency. So that's our second big thing, is that high pitch, high frequency, low pitch, low frequency. So loudness, amplitude, pitch, frequency. But that's not all there is to sounds, right? There's more to sounds than what's pitch and loudness. In fact, your ear, and let's be frank about it, your ear and your brain together are really, really sophisticated sound detectors. I mean, like on the telephone, which is a terrible conductor of good sound, you know the difference between different people's voices. Probably you could give, a sentence to be read by three people have them all read it into the telephone. You hear on the telephone, you know who is who. Well, what's going on? What is special about that sound that lets you know, like, oh, that's this sound and not that sound? Because it's a lot more than just how loud it is and how high and low pitched it is. So let's look at a sound that's not a simple sine wave. I brought with me my middle school trumpet. Of course, it makes me think of my middle school trumpet teacher who had so much patience. Mr. Naiman, if you ever see this, first of all, I'm sorry, and second of all, just in the decades in between, I have learned to practice. I know I never practiced when I was a sixth grader. Anyway, sorry for that. Let's take a look at how the sound of a trumpet looks. So I'm going to light this up. I'm going to back away this microphone so it doesn't saturate. Here's the sound of a trumpet. Woo, that was all. See, middle school. Okay, so I've frozen that sound. And let's have a look at it. So one thing that I notice about this sound is that it doesn't look the same as the other sound waves. It's got a really different shape. Before we go on to talk about the shape, I do want to notice that even though it's a really different shape, we do have a repeated cyclic pattern, just like the other ones. It's not as simple a pattern, but it's still a repeated cyclic pattern. That's what's characteristic of sound when it's not noise, right? If we hear noise like you don't see a repeated pattern. So we have this repeated pattern, and it's taking, I'm gonna say, like like I list this one, I was playing a slightly higher note, actually a similar amount of time. The period here also looks like it's around maybe a little less than 3 milliseconds, which means it's similar in period and similar in frequency to the other fork, or the first fork, which means it's simpler, one more time, which means it's similar in frequency to the second fork that we heard, the slightly higher pitched one. But how do we describe this funny looking shape? How do we say something about the shape other than like, oh, one looked really simple and this one looked really complicated, or like, oh, this has like this little bump and then like a smaller bump and then like a big bump and a big diagonal down, and it, that's not really a useful way to describe a sound wave if you were trying to repeat it or explain it to somebody or other else. So how can we describe a complicated sound wave with a little bit more precision? And in order to do that, we've got to look at it a little bit mathematically. Like, where could this complicated wave come from? This wave that still is a repeated thing, so we still are going to call it a wave, but it's not as simple as the other waves. To do that, we're going to look at a simulation of what happens if you can make multiple waves at the same time. So what we've got here is an arrangement where we've got sliders that go up and down that say, oh, like big amplitude, small amplitude. When you go all the way down, it's actually small amplitude, but in the other direction. So this goes up then down, this goes down then up, and we call that phase difference. But we have other frequencies present. We have these higher frequencies, and they're labeled, A1, A2, A3, A4, A5, where each one has a different period and a different frequency. So here's a simple wave, and here's another wave, and we can see both of them on the display. But here's the kicker. What happens when they play together? So I'm going to turn this off, and let's look at what happens when they look together. Now, I don't know if you noticed this, but this doesn't look like a simple wave anymore. This has two waves. It looks a little bit like our normal waves, but looks really different. We have another wave riding along with the first one. So now, like if I add a higher frequency, it's like, oh, look, there's a higher frequency riding along with the main wave. And we can put together a wave made up of lots of different frequencies that will make different shapes. So if I'm going to start just I'm going to put in the odd one. So look this, and a little bit of that, and look, we have an interesting, not regular looking wave there. We could do it with we do something here where we do alternate, and notice, I don't know if you noticed, but we're starting to get some of the, remember with the trumpet we had like a big bump and then we had some smaller things, and then we're starting to approach something like that, and we're doing it by having more than one frequency happen at the same time, more than one kind of wave adding together to make one wave. If we look at the individual waves individually, they look like this spaghetti thing right here. But if we look at what happens when they add all together, what we get is a wave that's complicated, but, readable. So we know that we have simple waves, tuning fork, complicated waves, trumpet. We know that it's possible to make more complicated waves by adding together multiple different waves of different frequencies. You put them together, you can get this more complicated wave. But that doesn't answer how we would describe the trumpet wave. I mean, we could make some guesses. And in fact, on this really wonderful simulation, they have a game, and I'm just going to pull this up, and you can play this on your own. You can go to the FET website and try this out. I haven't tried really hard, but honestly, I find it kind of challenging. So, this is really, simple. They're like, oh, can I match this wave? And I'm like, oh, gee, is it this frequency? No, it's not that frequency. Is it this oh yeah, it's that frequency, but oh, this isn't matching. Maybe I need to go with the other phase. So I pull it down. Oh, I'm getting close. Oh, I bet that's it. Let me check. Check answer. Yay! Right. Not a big deal. Okay. But if I try even level 2, I'm sure there are people who are really good at this. I'm not one of them. Okay, let's have a look at this wave. The question is, how do we make this wave? So I'm going to try some of this. Now, I think I want it to go up there and then, no. Wait, maybe this one goes up and that one goes, and then some of this. I mean, I'm getting closer, but like I'm having to do, oh wait, I'm doing a little better than I did last time I tried this. Just a little bit of this one. I don't know, will they is that okay? No. Anyway, see, I'm close, but like I've been trying at this for a while. Now imagine you were trying to do something, like if we go back and I say like, hey, what if there are 5 frequencies? Like if I'm trying to make this, I could be here guessing and trying to mix frequencies for a long time. So the answer is don't guess at what frequencies go into making a complicated wave. This is when we lean on math. And we're going to use math that we're actually not going to do the math ourselves, fortunately. You should just know that the math exists. And it turns out that there's a whole part of math called Fourier series. It's also mentioned, yeah, it's not, I mean, it's spelled French, sorry. Fourier series. And there's and Fourier series basically show that you can make any wave by a mixture of smaller waves. And there's a trick to working backwards called a fast Fourier transform. And there's lots of software that will do that. So let's have a look at what happens when we bring a fast Fourier transform, also known as an FFT, to bear on a complex wave. So I'm going to record the trumpet, but this time I'm going to record it into Logger Pro so I can manipulate it a little differently. Let's go. I got to push this button at the same time. All right. Oh, okay, so there's a sound. And yeah, if we zoom, let's just have a look. If we zoom in on this, does this look familiar? Kind of. So anyway, this is our trumpet. It's kind of complicated. How do we break it down into parts? Well, this is where we use fast Fourier transform. So in Logger Pro, I'm going to go Insert Additional Graph, FFT. Here's the FFT. And this is a really different kind of graph than what we've been looking at before. So notice along the horizontal axis, we have frequency. I'm going to change I'm going to take this, so maybe this is 4,000 here. Okay. One really good way of thinking about this graph is it's a recipe. It's essentially, how would I make this sound if I were going to make it up of simpler sounds? And so what this FFT is saying, and an FFT is sometimes called a frequency spectrum. A frequency spectrum. It's like all the possible frequencies, and then it's saying how much of that frequency is present in the sound. So right here, what we see is here's our first lowest frequency, and it's like, it's in the 350 hertz range. And then we've got this other frequency that is also happening right above 300. Then it's like there's not a whole lot going on up here. And then when we get to the next place where there's a lot of frequency, it is, sorry, I should put my glasses on. 690-ish. When we go next, the next one is 1054, and the next one after, and so each one of these frequencies has a different frequency, and the height of the thing tells you how much of that frequency is present in the complicated sound. So the FFT is a way of working backwards from a complicated sound to tell us what are the ingredients, if you will, what are the parts of that sound. So here's some terminology, and I said parts. I said it kind of accidentally, but it bears using here. We call each of these individual frequencies that are inside of this bigger frequency. So top wave is the regular sound wave. Bottom wave is the FFT, or the sound spectrum. And the bottom wave is basically saying how much of other simple waves does it take to make up this more complicated wave. We call those individual frequencies, we call them partial tones. Partial tones. Sometimes they're called partials. And this is, now I'm just going to kind of wave my hands at this because, as you can see, there are lots of frequencies present. But, you know, there's a significant one here, there's a really big one here, and then there's another one here. So maybe 1, 2, 3, 4, 5, 6, 7, maybe there's 7 really important partial tones, and then we can see some tiny little other frequencies that are present that our ears are going to pick up. I'm just not going to worry about them analytically. Like, your ears notice those things. But so this complicated sound is made up of maybe 6 or 7 individual partial tones. So terminology number 1, partial tones. Terminology number 2, our ear picks out the partial tone with the lowest frequency. So the first partial tone, now notice this is not necessarily the most significant frequency, but this partial tone here, that's what our ear picks out. It's the lowest one, and we go like, oh, that's the pitch of this thing. Because notice this is lots and lots of pitches, right? It's like all these different frequencies, and our ear doesn't go like, oh, there's so many frequencies. It goes like, oh yeah, that's about this high. Like, can I sing that high? No, yeah, I can sing that high, okay. But we're actually hearing a lot of frequencies at the same time. But we pick out the first one, and it's called the fundamental frequency. And our ear kind of zeroes in on the fundamental, and that is the one that we say is the frequency that's defining how high-pitched this sound is. Even if it's not the most important partial tone, we still, our ear and brain together, pick that up and go like, oh, that's the pitch of this thing. All of the other partial tones, in terms of our perception, don't add pitch, they add quality. They affect the timbre. They tell us, what does this sound like? They tell us, this does not sound like a guitar. It does not sound like a tuning fork. It doesn't sound like a piano. This sounds like a trumpet. Like we pick up all those different partials. In fact, different hairs inside of your inner ear are shaking for each one of those partials, and that's triggering nerves that are going to your brain. Your brain goes, oh, trumpet, I've heard that before. They're all partial tones. The lowest one is the fundamental. Every partial tone that is higher pitched, has a higher frequency than the fundamental, is called an overtone. They're called overtones. And there's something special about most of these overtones. Like, I don't know if you've noticed on this graph, but they're very evenly spaced. They're very evenly spaced. I'm going to see, can I make this thing make you bigger? No. Okay. Oh. How about that? Okay. So I'm going to point to these partials, and notice this is a little bit touchy because, you know, this thing is kind of wide. This is actual data. This isn't just pure math saying like, oh, it's this frequency. And so, you know, if we point to this thing, I like to point to the pointiest peak in the middle. And this is saying 347, I'm going to call it 347 hertz. So our fundamental is about 347 hertz. Okay, where's our first overtone? I'm going to point to this, that middle bit of it. If you were doing this yourself, you could zoom in to be really precise, but I'm just doing it here. And it goes 693. I don't know if you noticed that like 347 and 693 are very closely. In fact, if you double, stop me if I'm wrong, 347 times 2 is 694, and the first partial is at 693. Not a coincidence. And if we go to the next one, and it's 1049, now I don't have a calculator handy and I don't add that fast, but I guarantee you that this third partial has a frequency that's 3 times the fundamental. and this one has a frequency that's 4 times the fundamental, and so on. Not all overtones are like this, but these overtones are characteristic of most musical instruments. Like we actually, our ears kind of like this kind of sound where they're integer multiples of each other. If an overtone is an integer multiple of the fundamental, it is called a harmonic. So that's a harmonic frequency. All right, so vocabulary so far. We've got partial tones. That's all of the different parts, all the different frequencies that go into making our complicated wave. Fundamental frequency, that's the lowest one, the one with the lowest frequency, not the lowest amplitude. We've got overtones, that's all the higher pitches. Then we've got harmonics, which are any overtones that are an integer multiple of, meaning 2 times, 3 times, 4 times, not like 12.5 times, but an integer multiple of the fundamental. Those things are called harmonics. Now we can have overtones that are anharmonic overtones, which is to say not harmonic, which is, like they're higher than the fundamental, but they're not an integer multiple. I guarantee you, like if you heard them, you'd be like, something sounds weird here, because they just sound weird to our ear. But those are the basics. Like, so when we want to describe a more complicated wave, we describe it by describing its partials. And I'm going to do a really vague job here, but if I were going to break down this trumpet, last time we said like, oh, how could I describe the wave? Like if I go to the actual sound wave itself and go like, oh, what is it? It's got like 2 little wigglies and then like a steep up and then this kind of diagonal down, and like a terrible way to describe a wave. On the other hand, if I say, oh, how do I make this wave? And now I'm going to make this bigger. I have a wave that has a fundamental frequency of 343 feet, around 350 hertz. And then I have a first overtone that is about 5 times as high, so 5 times the amplitude at the first overtone, at twice the fundamental. And then I've got a second overtone, third partial, second overtone, that is 3 times the frequency of the fundamental, but that goes without saying. We just say second overtone. And we can say, oh, the second overtone is, 4.5, and whereas the fundamental is around 2, so it's like a little more than twice as strong as the fundamental. So we can describe a sound by talking about the relative strengths of the harmonics. The relative strengths of the harmonics. So this is a really good way of describing complex sounds, and it's how we do it. We talk about like, oh, are there even harmonics that go on and diminish really fast in their amplitude, or are they odd harmonics? This is a very characteristic waveform that actually has a low fundamental and a really big second harmonic first overtone, and that pattern is really what we hear. I mean, nobody's brain is reading out to them like, oh, this is the value of all of these partials. But literally that's what your brain does, and then recognizes trumpet. So that's complex sounds. There are lots of tools that you can use to perform a fast Fourier transform that will produce a sound spectrum from a sound. Logger Pro is one, phyphox is another good one. Both of these things are really great in the lab for analyzing complex sounds.